So this is Class Notes D in Lesson 1, and there was a lot of stuff going on here right before we got to Class Notes D. So what I'm going to do is actually review a little bit of that as we go ahead and fill in Class Notes D. So what were we trying to do? We were trying to solve this non-homogeneous first-order linear ODE by using this unknown function mu. And that is part of what Class Notes D is going to help us do. We are going to figure out what this function mu is. And what were we trying to do? We were trying to say, well, ultimately what we want to do with this first order ODE is we want to integrate it, right? Y is kind of trapped in a derivative. We want to undo the derivative. That's integration. To do that, though, we need to get to a point where we somehow down here, right, have a derivative of something involving y. And then we can just get rid of the derivative by integrating, and then we can solve for y. So that's kind of the idea, and the rest of this process in between is what we have come up with, we mathematicians, as a way to get to this point, right? So let's figure out how to work everything out. So the first step that we talked about in this process here was multiplying the non-homogeneous fold by some unknown function mu. Great, so that's just when you multiply every term by mu. And the second step, find the mu function that collapses the left-hand side into the derivative of the product, mu times y. So this is where I want to start, right? This equation is how we are going to figure out what mu of t is. So what are we doing? We are going to try to find a function mu of t such that the derivative of mu times y is equal to mu dy dt plus a of t mu times y. Why? Because, again, that left-hand side would become the derivative of mu times y, and then would get us over here. And then, like we talked about earlier, it would be able to get rid of the derivative by integrating, and then solve for y by dividing by mu. Great, so let's declutter things a little bit here. Nice. And then let's figure out how mu is going to emerge from this equation. So what I'm going to do here is take this derivative here by the product rule. So product rule says derivative of the first times the second plus the first derivative of the second. Great, and then I want to make all of these terms equal, so I'm going to set these two things equal here. So I have y d mu dt plus mu dy dt equals mu dy dt plus a of t mu y. And certain terms cancel out, right? So when things start canceling out, when things start canceling out in a equation, generally that's math telling you that something is going right. So these terms cancel out here. They're both mu times dy dt. So what are we left with? We are left with y d mu dt equals a of t times mu times y. Great. So technically, there's one thing to mention here. So I would want to divide by y, right? And then be left with something that is simpler to analyze. But I just want to mention one thing here, right? Generally, you don't want to divide by functions or variables because you are assuming that they are not zero. So I want to do a quick little aside here. For example, what if I want to solve x squared equals x? Just to illustrate this point as a public service. You might say, okay, well, I'm going to divide by x on both sides. Great, sure, let's do that. Why not? Then you get x equals 1. You say, okay, fine, I found the solution. I'm done. There's nothing left to do. I'll go home. The problem is that misses the solution x equals 0, right? And why was that solution missed? Well, because we divided by x. And dividing by 0 is not allowed in math. So that is generally not a good idea, right? So we want to go back and solve this problem a bit more generally so that we capture this other solution x equals 0. And how would we do that? Well, we would resist division by the variable, right? We would try to do everything that's all the other arithmetical operations. We want to factor, for example, multiply, add, subtract. So we would bring over the x, and then we would factor, and then we would get this form. And now we say, oh, okay. So the product of these two quantities is 0. Either this one is 0, or this one is 0, or both, right? And then we are back to capturing the solution, the extra solution that we missed by dividing by x. Okay, so again, that was a very, very quick little aside because it's very relevant here. So if we go back to what we were doing, we could try the same thing. We could divide by y, right? But then we would lock ourselves into just this implicit assumption that y is not 0. Okay, so I don't want to do that. So what I'm going to do is a version of what I just did with this little example problem here. So I'm going to take these terms and put them all on the same side and rearrange them a bit just so that we can see more clearly what is going on. Okay. Minus a of t mu equals 0. Great, so at this point we can see, similarly to what happened over here with this other term, that we are in a position where the product of two things is 0. So we have to consider both possibilities. What if y is 0? And then what if this thing is 0? Okay, so I'm going to scroll up a little bit here to think about what if y is 0. So where did we originally start with all this? Well, we were back into this particular non-homogeneous fold. So what happens if y is 0, right? Let's just assume y is 0. All right, so what would we get? We get 0 plus 0 equals b of t. Okay, fine. So that would force b of t to be 0. Okay, so then what happens? We have 0 equals 0. So that is not very useful or illuminating. It does not help us understand how to solve non-homogeneous folds. And it literally tells us nothing. So sure, fine. So we have taken care of the case when y is 0. And it has turned out to not give us any additional information. So that's fine, right? That may happen. It's not as illuminating as what happened over here with the x squared equals x example. But again, I mentioned that because this is lesson 1, and I want to set the stage for reconfiguring your thinking a little bit about how you might approach some of these algebraic manipulations and try to help you be more expansive in your thinking of some of those operations. Great, so we have considered the y equals 0 case, and that does not yield any useful information. So then we're going to say that from here, right, from here, this implies that d mu dt minus a of t y, a of t mu equals 0. Okay, so this is a very interesting form for mu. Why? Because, well, let's think about it, right? This is an ODE for mu, which is this unknown function we're trying to find. And let's classify the ODE. This is a first order ODE. And here is mu appearing linearly, no mu squares, no sine mu's, none of that. It's being multiplied by something that looks like our a of t function, except it has a negative sign here. And then the right-hand side is 0, which is definitely a function of t. So long story short, what I'm trying to point out with all of this is that this is a homogeneous fold. Okay? So this is very cool because we know how to solve those, right? We've been doing that for a while. So the solution is mu of t equals some arbitrary constant. And let me move things down here a little bit. The solution is going to be an exponential, involve an exponential, which is what we have been seeing from solving homogeneous first order linear ODEs. So what's the solution? K e to the minus integral of whatever's here, minus a of t dt. Okay. You might be saying, how did you know that right away? Right? Did you not have to solve this? And the answer is yes and no, right? So I'm scrolling up here in the notes, pardon the scrolling a little bit, and here's where I'm going. So at the end of the second module, I believe, yep, right before the start of the third module, there was a recap that I put in here for solving a homogeneous fold, right? So if I have a homogeneous fold, these are the steps, and here is the general solution that you get. So that's what I'm using, right? So if you know what the a of t function is, you literally just plop it in there, you integrate it, multiply by a negative sign, exponentiate, multiply by k, and that is your solution for y. So I am using this end result down here when I am solving the mu ODE that we've arrived at. Okay, so that's how I get this form for mu. Great. So then the last little thing I'm going to do here to simplify this is notice that this minus sign and this minus sign, they go away, they multiply each other, right? So I'm going to try to get rid of these. Great. And then one more thing to notice, once this function has been worked out, right? Whatever a of t is, you'll know that by the specific problem you're trying to solve. You will integrate it, you will exponentiate it. So this thing is going to be a function of t, right? Generally, it might be a number, and it's going to be multiplied by k. So k, you remember, is kind of left over from the plus c in integrating in first order ODEs. But if we look to what's happening in this context, so what happened with mu initially is that we were trying to solve this non-homogeneous fold. And then what's the first step we did? We multiplied by mu. In other words, every term in the ODE gets multiplied by mu. So now that we have figured out what mu is, right, that k number is going to appear in every single one of these terms. Okay, and that k number, because it's in every single one of these terms, does not matter, right? We can divide by k, and that will get us to exactly the same place as if we had k in there. All right, so long story short, we do not need to worry about the k in here, right? It doesn't matter what value for k you choose. This family of mu functions achieves what we want it to do. What is that? Achieves step number 2 up here, right? Find mu of t that collapses the left-hand side into a derivative, right? So we have found an entire family of functions that does that. But because of the way that mu is acting in the ODE by multiplying every single term, we don't need to keep that freedom in choosing an entire getting an entire family of mu's. So we are going to set k equal to 1. So our final form for k is e to the antiderivative of a of t dt. That is why, and scrolling down a little bit here, we see this definition. So if I want to solve a non-homogeneous first-order linear ODE, looks like that. The function mu defined by this is the integrating factor, right? So that's where this particular form comes from all of the work that we just did to get us to this final form for mu. All right, so that is the end of class nodes D.